to go over every topic because there's just so much here all day.
Can we do more with the mathematics?
Sure, yeah. So first, let's look about the exam. It's 50 questions, but I know that's a little more than I said, but I worked through it pretty quickly. Like, it only took me about 20 minutes to work through it, but you know, I know how I wrote the questions, so I know them and I worked through it really fast. But like, if you know it down really well, you can finish it probably in 45 minutes. But I don't expect you to, so it'll probably be more like an hour and a half. And then we'll do the assessment afterwards. So I'll probably just give y'all until 3:30, or if you're in the online section until 5:30, give you 2.5 hours in order to finish both of them. I'll give you plenty of time. Okay? So let's look at this test. The exam largely comes equally from the 4 exams, as I told you, and I will change up the questions some. So for example, this is the first question on the test right here, but it's slightly different. It's not exactly like this. So there are some ways that you can change this, give different quarks or give different particle, like this is for a neutron, it could be for whatever. So anyway, that's going to be the first question that you see on the test, but it's rewritten just a little bit. All right. Do we want to do some of the calculation problems on this exam? Okay, well, you are going to have 2D force problems, so let's go straight to that. This force problem was actually pretty straightforward because the forces canceled out. So on this, it asks for the net force on the 2 nanocoulomb charge. And the net force due to this particle is going to be in this direction, and the net force due to this particle is in this direction. And because they're equidistant and because they're the same charge, these 2 forces will cancel out. So all you're left with then is the force due to this particle, which is in this direction. And then that becomes a fairly straightforward problem. You're just doing F equals K QQ over R squared. And you could see something like that, especially if you see something like this with a whole bunch of particles, you need to start looking for ways to simplify it. Because I'm not going to give you a problem with a whole bunch of particles like this and ask you to do the vector addition. Right? There's probably a way out. Okay, let's look though at a, yes? Yeah, Coulomb's constant is on the equation sheet. Listen, you really need to be aware of what's on that equation sheet. So Coulomb's constant is up here amongst all the constants. It's right here. But then there are others that you need as well. So you have the mass of the electron and the proton. That might come in handy. This is the permeativity of free space. Use that for determining capacitance. Let's see. This is I don't know what it's called. Anyway, you need this for determining the magnetic field that comes up in chapter 5. Speed of light, per unit of charge. So you have constants here. You have constants in the chapters too. What's that? No, it's not angstroms. I forget what it is. All right. Also, as usual with my tests, it's laid out by chapter, or actually it's laid out by exam. So, you know, exam 1 was like chapters 1 and 2, I think. So the first part of the exam is going to be chapters 1 and 2. And so use that as a guide for you to sort of shift gears as you're going through the exam. And it does come in order of the topics as we do in the class, or as we've done during the year. Okay, so let's go back to this. Let's look at the other type of problem, which is a 2D problem. And you will have a 2D problem, and it's going to be something similar to this, where I have 2 charges, essentially 3 charges, and I ask you for the field, the force, the field or the force due to that configuration of charges. You need to read it carefully, and make sure that you get either the field or the force. We're looking for the field here. Remember the electric field, the magnitude is KQ over R squared. And here I'm looking for the field at point A. Now if I was looking for the force, I would ask you for the force on this particle or this particle, because the force has to be acting on another particle. But if I'm asking for the field, I ask for the field at a particular point in space, not necessarily where there's a charge. Okay, the first step on this is to draw the field vectors. The field due to this particle, I put in have an imaginary positive charge here, and I ask myself, what is the direction of the force on that positive charge? And it's going to be in that direction. So I'll call this E1, and then the field due to this particle is in this direction, and I'll call that E2. Okay? Go with me, because if I put a positive particle here, imaginary positive particle, it'll be repelled from this particle. So the electric field then is in that direction, away from this positive 2 nanocoulomb charge. Okay, and then I calculate the magnitudes. E1 is K, Q over R squared. That's 9 times 10 to the 9th. Q is, we're doing E1, is 1 times 10 to the minus 9 divided by 3 meters squared. Look for things to cancel out, because I like to make the numbers just easier to work with, especially on these type problems. So look for things to cancel out. Those two cancel, 10 to the 9th, 10 to the minus 9th. This cancels with that, and it just leaves me with 1. You're not going to get all even numbers, but on the test there are a lot of even numbers for you to deal with. So it just makes it easier dealing with the calculator. All right, so that E1 is equal to 1. Do a similar thing with E2. E2 works out to be 2 newtons per coulomb. Okay? Is it okay if I not do that? Yes. Can I finish this one? Yeah. All right. And so then I know E1 and E2. And I have to determine the direction of E1 and E2. All right. Add up these two vectors. I'm sorry. So now I find the magnitude. I do the square root of 2 squared plus 1 squared. And that gives me 2.2. But then I also need to know the direction of that. So if I draw my coordinate systems here, I have my vector E1 in this direction and my vector E2 in this direction. And I want to know this angle right here. In order to find that angle, I say the inverse tan of E2 over E1. That's 2 over 1, and that's equal to, I don't know what it is. Uh, 63. Yeah, so it's 63 degrees below the positive x-axis. Make sure that on these problems you watch closely those qualifiers, because here's my 63 below the plus x-axis. There might be some distractor answers that have maybe the right number but the wrong qualifier. So make sure that you look at that. Think about which quadrant it's in. Okay? You will have a 2D problem. Make sure that you can work them out. Work with these vectors in 2 dimensions. Okay? Y'all good on that? If you're not, make sure that you go through and practice some of those 2D problems. And good practice is, if you see a problem like that in our test, after you work through that and sort of feel like, gosh, I need some more practice, you can go and look at the other old tests, and they're often very similar questions. So I'm not telling you to use the other old test, but unless that material is on this exam, and then you can go look at the other old test. Let's look at number 14. Number 14, at what point is the electric field 0? And point C is equidistant between the charges. On these, you just need to go through and think about what is the direction and the magnitude of the electric field for each charge. So for example, you all remember what the answer to this was? It was B. All right, let's start at A then. So I'll do the electric field due to this particle in blue, due to this particle in red. So the electric field due to the plus 2q is in that direction, due to the plus 4q is also in that direction. All right. I drew them the same magnitude because even though this charge is bigger, or smaller rather, I'm further away from the big charge. So as I move further away, the electric field decreases. E is kq over r squared. Now if I look at E, or let's look at C, for example. C, the electric field due to this one, is in that direction. The electric field due to the 2Q is in that direction. Notice that I drew this smaller. Point C is equidistant between these two charges, but the plus 4Q exerts a bigger electric field at this point because it has a bigger charge. So it's not C. C is not 0, and a lot of students put that. But if we look at B, at B, I'm closer to the plus 2Q charge and further away from the plus 4Q charge. So that is a point where those two electric fields can cancel out because I'm farther away from the bigger charge and closer to the smaller charge. So I can have my electric fields become equal somewhere in this regime between the middle over here in this area. So B is the only possible answer. If you do the same for D, you find that this charge dominates the electric field because it's so darn close. And then over here, the electric field for both of them are in this direction. So the electric field cannot be 0. These types of questions are good. You can change them a little bit. Like I can just change the charge or change the configuration, like make this a plus 2Q, for example. By the way, if this was plus 2Q, where would the electric field be 0? It would be C, right? So think about that, how you can change those questions in particular ways. Okay? Does that answer your question? Clear? All right, what else, folks? So, number 19, awesome. Okay, this is another similar question. This one's a little more straightforward, but you want to know where is the potential equal to 0. Now remember, potential is a scalar quantity, so I'm not worried about vectors or anything. Our potential is KQ over R. And if I have two charges, say this is plus 1, this is plus 1, the potential, plus 1, and we'll say the other is minus 1, the potential is 0 when I'm equidistant from both charges. So like right here, I'm the same distance here as I am here, so that potential is equal to 0. Similarly, right here, I'm equidistant from these two charges, so the potential is 0. The reason is that when I add these up, I get KQ over R plus K negative Q over R, and this equals 0, as long as R is the same for both. If R changes, then these are not going to be equal and opposite. And so in this one, I'm looking for a point where the positive and negative charges are equidistant from one another. So for example, here, oh, this is the answer, I guess. Oh wait, no, that's not the answer. So those 2 points are equidistant, their potential is equal to 0. These 2 points are equidistant, their potential is equal to 0. And these 2 points are also equidistant, their potential is equal to 0. But look, that is true for all these. Equidistant, equidistant, equidistant. So the potential at all these points is equal to 0. You can change this just by jumbling up the charges. And if you jumble up the charges, you get a different answer. It could be just one of the points, it could be none of the points, it could be whatever. All right, Casey? All right, let's look at the others. Which others of these? Number 24 is another one. You have to find the potential at point A. Look for our special triangles, right? 3, 4, 5 triangle is a pretty common one. But if you don't remember that triangle, just do the Pythagorean theorem. Square root of 3 squared plus 4 squared, the square root of that gives us this distance. We need this distance because we calculate the potential is KQ over R. So I do the total potential is the sum of the potentials. It's going to be K times negative 10 times 10 to the minus 9 over R, which is 5, plus K, or I'll go and write out 9 times 10 to the 9th, times 5 times 10 to the minus 9, divided by R, which is 5. I get some things canceling out here. I'll do this 9 times 10 to the 9th. Look for that. These cancel. These cancel. This cancels. and this cancels with this and leaves a 2. And so I get negative 18 plus 9 is negative 9. All right? Finding the potential. You could see something like that for sure. How to calculate the potential. All right? Y'all good on this? Eh? Okay. I'm going to clear this. What else on this test? You know your field lines, your equal potential lines, what they mean, how to calculate force, field, and potential. We had a little bit of capacitor on this test, stuff, about the dimensions of the capacitors and the charge on a capacitor, that kind of business. Practically every topic is covered on the final. You want to look at the next one? Okay. On exam 2, we have capacitor circuits. You'll see capacitor circuits and resistor circuits. We have 3 different types. We have, the combination capacitor, combination resistor, and then the multi-loop circuits. I think you have all 3 of those on there. So circuits, the basics of your voltmeter and ammeter, Ohm's law. Ohm's law again. Resistivity. Power and how it relates to our household items. Combination circuits like this. Stuff about your house. Make sure you understand those 3 systems we talked about and the basics of your house. Resistors in series and parallel. You have RC circuits, being able to calculate those. Just make sure you know what's on the equation sheet regarding those and that you're able to use them. Also know how they act over time. Multi-loop, you're going to have a multi-loop. It'll be just like this except a different circuit where you have to find the equation and then you have to calculate the current. Those 2 are on the test. All right? Any of these stand out to you in particular from exam? The multi-loop? And Casey, what were you going to say?
Number 3, I thought it was I don't understand.
Okay, let's go to number 3 and then we'll come back to the multi-loop, okay? Okay, so this one right here. What is the charge on the 6 microfarad capacitor? So a couple ways, the not the hard way, but the way that's always going to work is you find the equivalent capacitance. The equivalent capacitance is 2 microfarads. Remember, it will help you to remember those common fractions that we use. If I have a 3 and a 6, 1 over 3 plus 1 over 6, that's equal to 2. 1 over 4 plus 1 over 4, that's equal to 2. 1 over 2 plus 1 over 2, that's equal to 1. 1 over a third plus a third plus a third is equal to 1. And then 1 over a third plus a half plus a 6 is a 4 plus 6 plus 2 is equal to 1. So it'll help you to just be familiar with those fractions because you'll see them pop up. And here we see it pop up so that when you come to this, you can say, oh, a 3 and a 6, that's equal to 2. Okay, and it will come up several times, those different types of fractions. Don't memorize them, just be familiar with them. So anyway, my equivalent here is 2 microfarads with 12 volts. Then the charge on this capacitor, Q is equal to CV, is 2 microfarads, 12 volts, 24 microcoulombs. And then that's the answer. Because capacitors in series have the same charge. And whatever charge is on this capacitor is also on this one and this one. So I have 24 microcoulombs here. I also have 24 microcoulombs here. By the way, then we could take it a step further. This question doesn't ask it, but we could take it a step further and find out what is V. V is Q divided by C. And so I'd do 24 divided by 3 is 8 volts. 24 divided by 6 is 4 volts. So you could do that. Another way, if you're a little savvier, you can say, well, this is the big capacitor, So it has the small voltage. That's the way it is with capacitors, not with resistors. It's the opposite with resistors. But this is the big capacitor, so it has the small voltage. This voltage has to be half this voltage, and they have to add up equal to 12. So 8 and 4 is going to work. All right. Those types of relationships come up a lot in circuits. I like to use them just to make it easier. So, if you have to, just do this calculation, and that's fine. It won't take you that long. You'll have plenty of time. But if you can get savvier with it, then you can go through that little shortcut. Does that help a little? Practice your circuits, because they're going to be on there for sure. You have several circuits. Okay, and you want to do the multi-loop? The equations are the 22, 23, or 24, are all of them.
I think it's 22, the pattern.
Okay, the 22, we're looking for which of these is the right equation. Remember, if I'm going for the batteries, if I'm going in this direction, it's positive. If I'm going in this direction, it's negative. If I'm going with the current, it's negative. If I'm going against the current, the change in potential is positive. So you need to remember those rules, and that's how you approach this. So then I'll look at each equation. I have 3 minus 2i1. So that means I'm going in this direction because it's positive 3. Minus 2i1. That's good so far. Plus 6. Okay, that's good. And then I do this whole thing where I go down here. I have to go back to the beginning of where I started. So A isn't right because I have these extra terms right here that aren't part of the loop.
Yeah, I have a question on minus 2i because I felt like it's going with the current, but it was against.
If you're going with the current, the potential across the resistors is negative. If you're going against the current, the potential is positive. Resistors, that's what they do. They take away energy. And so if you're going with the current, they're doing what they're supposed to be doing, which is to take away energy.
Now we know what it is.
Okay, yeah. And then here I have 3 plus 2i. 3 plus 2i. Oh, it shouldn't be that. It should be negative 2i, so it's not that. Here I have I1 plus I2 plus I3. I just pick a junction. I1 is coming in, I2 is coming in, I3 is going out. So it should be I1 plus I2 equals I3. So none of these work. It has to be D. Let's just double check. I have 5 plus, going in this direction because it's positive 5, plus 6i2 going against the current, so it's positive, minus 6, going from big to small, so it is minus 6. So that is the right equation. And then for the next question, it asks, what is the direction and magnitude of I2? Well, if you got this one right, then the next one was super easy because I've already given you the equation. You just say 5 plus 6i2 minus 6 equals 0 and solve for I2. So I get I2 equals 6 minus 5 over 6. 1/6 amps. Since it's positive, it's going to be to the right. Oh wait, no, I2 to the left. That might not be the case that you have the equation that you need to solve for the current, but if you don't, what you want to do is pick some loop within the circuit that's missing a resistor. So here I want to know I2. I'm going to pick this loop because when I pick this loop, I don't get I3 in that equation. Notice here I only have I2. If I were to take the top loop, which I could have done, I'm going to get I1 in that equation because of this resistor. So you just pick a loop that doesn't have a resistor. Otherwise you have to go through and solve a whole system of equations, which I'm not going to do for these tests. Okay? That helped a little bit. Yeah. So for example, on this one, you're supposed to find one of the currents, think through the 2 ohm resistor. Which loop would you choose to find the current through this resistor? The left or the right loop? The right loop, right. Since there's no resistor over here, you'd write an equation for the right loop, not the left loop. And then the big loop, it doesn't have this in it anyway, this current. All right. Anything else on this exam? Yeah.
Can you do the, I think it's like 10 or 11.
Sure thing. This one right here?
No, about it.
Yeah, okay. Well, let's look at 11 too when I'm done, because that one's a little bit tricky. Well, let's look at 10 right now. You want to find the resistivity. So my resistance is equal to rho L over A. That's on your equation sheet, and I'm looking for the resistivity. And then once I find the resistivity, I can pick what is the unknown metal. So I look up here to figure out what I need. Here's my A, here's my L. Well, I don't have R, so I need to figure out what R is. From Ohm's law, R is V over I. Remember, this is V equals IR, which is on your equation sheet. So Ohm's law is R is V over I. So that's going to be V, which is 20 volts right here, divided by 10 amps. So that's 2 ohms is my resistance. And so I solve now for rho. It's going to be RA over L. I just multiplied both sides by A over L to solve for rho. And then I put in my values. I have 2 ohms. I have my area, 5 times 10 to the minus 8. My length is 1, and that gives me 10 times 10 to the minus 8 ohm meters. And I come along here, and it tells me it must be iron, because that's what has that resistivity. So on these couple steps, you first have to find the resistance, then you have to find the resistivity, and then once you find the resistivity, you just go in the table and select out the material that has that resistivity. Let's look at number 11 too. It's a little tricky. A lot of students missed it. Can I clear this? And then we'll move on to the next exam unless you have more questions. So here, I need to know the voltage of the battery. And I tell you that R1 has 8 volts. Okay? You want to make this into a simplified circuit. So I have my first resistor, and then I want to know what is this resistance. Well, here I have 6, 3, and 2. Gosh, a 6, 3, and 2 in parallel. What is that? What is it? It's 1, right. So I have 1 ohm, and this is 4 ohms. This is just 1 over 6 plus 1 over 3 plus 1 over 2. The inverse of that is equal to 1 because it's like 1 over 12 over 12, which is 1. So I have 4 ohms and 1 ohm. If this is 8 volts, what must the voltage be here for this resistor? Well, this resistance is a quarter of this resistor, so this voltage is going to be a quarter of this voltage. So what is it going to be? 2 volts, right. And so if I have 8 volts and 2 volts, this must be 10 volts. Another way of doing this would be to say, if I have 8 volts and 4 ohms, that's 2 amps. And if I have 2 amps, I also have 2 amps over here. If I have 2 amps over a 1 ohm resistor, I have 2 volts. And then that would get you the 8 plus 2 is 10. Okay? Anything else from this test, Joe? Let's go into the next one. What was this? Magnetic fields and stuff. I'm just going to scroll down through. Y'all take a look and see what you think. Yeah, there are only a couple of right-hand rule problems on the test. So, like, for example, this one right here. I want to know the direction of the force. I let my fingers go in the direction of I, my index finger, and then my middle finger goes in the direction of B, goes like that, and then my thumb gives the direction of the force. So the force on this is into the page. Here, this right-hand rule is a little bit different. I let my thumb go in the direction of the current here, and then my fingers wrap around and give the direction of the magnetic field. So the magnetic field here is to the left. This might make a little more sense to you if you look at a cross-section for number 8. So if I imagine a cross-section with the current traveling, what's that, counterclockwise, I imagine my thumb going on one side in the direction of the current, then the magnetic field goes into the page on this side, out of the page in the middle, which is where we really want to know what is the magnetic field. So the magnetic field in this case would be like that. In this case, it's going to be to the left for a similar reason. Thumb in the direction of the current, my fingers point down the middle of that coil, that solenoid. It's on this exam, so yeah, you could see it. You could change it just by changing up the direction of the current. I could also give it as a cross section, like I did over here. It's a little bit easier to see with the cross section. It's kind of hard to visualize here. Yeah, but just imagine, right? There's two sides to this coil. There's the coil, the side that you can see, and then the back side. Just worry about the side that you can see, right? Thumb in the direction of that current, and then the magnet, it curls into inside the solenoid. If it was going the opposite direction, it would be like that. If the current was going the opposite direction, it would be like that. Don't forget to use your right hand rule. Your right hand, like sometimes I see students and they forget their left hand.
I was using my left hand.
Yeah, just tie it behind your back.
It's hard for your left finger because like everything's balanced.
All right. Okay. Okay, sure. So this is a two-step problem, but it's still right-hand rule. Our force, we need to just draw our vectors here. My velocity vector is in that direction. My force vector is in that direction. So you want to ask yourself, what is the direction of the magnetic field? So V is in that direction. F is to the right. You're right. And so the magnetic field is into the page. So the magnetic field that causes this motion is into the page. And then you ask yourself, what's the direction of the current? Well, which is it? I mean, it's either like this or like this. It looks like it's to the left, right? Because if I have my thumb in the direction of the current, they go into the page on this side, out of the page on the other side. So it has to be to the left, A. Those are good right-hand rule problems. You'll see similar things. There were 2 or 3 that were right-hand rule. But you know, 2 or 3, that's a half a letter grade on the exam. So. A little bit of light stuff, history of light, diffraction, reflection, speed of light, mirrors, ray diagrams. Sure. Concave mirror. Yeah, it will help you to know your properties of mirrors. It'll help you on several questions. So also with your lenses. But if you get your mirrors, the lenses are similar. They're a little bit different, but they're similar. So with the concave mirrors and the convex mirrors, you have 4 total. Really, there's only 3 that you're concerned with, because one of them is no image at all. And remember, concave mirrors, the analog in lenses is the convex lens. Sorry, that's what it is. So concave mirrors, I have 3 situations. Convex mirrors, I only have 1. If my object is outside the focal point, my image is real and inverted. Inverted images are always real because, you know, M is negative Q over P. In order for this to be negative, this has to be positive. And a positive Q is a real image. So the real and inverted image, if I'm at the focal point, I have no image. So you're not going to, I guess you could see that. But if I'm inside the focal point, this is my object. My image is back here. It's my object, my image. Okay, here I have a virtual, upright, bigger image. It's always bigger. This is like your shaving mirror. When you bring your shaving mirror up close to your face, it makes you bigger. It's always bigger. With the convex mirror, this is my object, my image is virtual, upright. Virtual images are always upright because if Q is negative, M is positive. And here, this is always smaller. You have very similar things, practically identical actually, with this is concave mirrors. You have identical with convex lenses and concave lenses. They look a little different, but it's identical in these properties of the images that you form with them. Okay?
Will you mix those in problems? Like you did
No. What do you mean mix them?
like will you put a problem where there'll be like a lens and a mirror in it and she doesn't figure out which is which? Sort of. Like for example, in the beginning, so you're gonna put a mirror question, and then like later down it's gonna switch from like mirror, like instead of like mixing.
Yeah, I can. Will the mirror questions come before the lens questions?
Yeah, like they're not gonna be in the same question together at all.
Say, like, number 35 will be about lenses and mirrors? No. No, that won't happen. That would be confusing.
Yeah.
But they are kind of confusing because they're similar, but a little bit different. Don't forget that with concave mirrors and convex lenses have a positive focal length. With convex mirrors and concave lenses have a negative focal length. I won't tell you that, you just need to figure it out. And often, or not often, but on some of the problems I won't tell you what type of lens or mirror it is. I'll tell you if it's a lens or a mirror, but I won't tell you what type it is. And you have to go back through these different things and say, oh, the image is smaller and upright. That must be a convex mirror. That's a virtual image. Or my image is bigger and upright. That must be a concave mirror when I'm inside the focal point. Or I have a real inverted image. That must be a concave mirror. Okie dokie? Good. That's good to know. It'll help you on several other questions to know those things. Your ray diagrams, you know, they'll be similar but different. I'm only going to give you this or the convex lens like we had on the last test. I'm not going to give you different lenses, but I might draw them slightly different. You always need to know that, you know, this is the correct ray, parallel through the focal point, and through the focal point and parallel to the axis is correct. Well, number 1 is correct too, actually. Yeah, for mirrors, I go through the center of curvature and it comes back on itself. So all of these are correct on this one.
Is number 3 wrong? Because it goes.
Oh yeah, it goes through the center of curvature. Yes, number 3 is wrong.
Why is number 2 not in the focal point? Is it just so you can see the focal point?
I think that is. It hits the focal point, sort of. I think it's just a little bit. Okay. Number 3 is wrong because it goes through the center of curvature, not the focal point.
Oh, okay.
Yeah, be careful with that.
Oh.
I thought it was right too. Yeah.
Yeah, I have another question. So, do we only have to remember like the easier ray diagrams? You know how you would.
Right. That's what I told you. Yeah. So only concave mirrors or convex lenses when they're outside the focal point. Just like the ones. It's just I like redraw the rays. Okay. You only have one of those. Either the mirror or the lens. I can't afford you. Okay. Good on this test or what? Scroll back through.
I guess 19 or something like.
Fiber optics? Well, you just need to know, in order for total internal reflection to occur, the outside index of refraction has to be less than the inside index of refraction. So for example here, going from air to water, if I think about my rays coming, when they go into the air, they're going to speed up, because light travels faster when the index is less, 1.3 for water, and that's going to allow for my ray to go to 90 degrees. But if I was traveling from air to water, it would bend the wrong direction, the light ray, and you can't get total internal reflection. And so down on this next one, in order for this to occur, the index of the cladding has to be less than the core. Think about fiber optic cables, they're just glass, and they don't have to have anything on the outside, so it's glass surrounded by air. The index of refraction of air is less than that of glass. So this always has to be less than this, the index. All right? Nobody's asked me about what I think are the two most difficult questions, number 16 and number 24. Really? Neither one difficult?
The mirror when it comes to knowing yourself.
24 is hard.
How do you know if it's on the right or left?
Well, let's look. There's a lot here. So a mirror produces an upright image. The object is 8 centimeters high. The image is 16 centimeters high. So that means that I'm dealing with a concave mirror. How do I know that? Well, go ahead. Right. A positive 2 magnification. The only type of mirror that can make a positive 2 magnification is a concave mirror. An upright, bigger image has to be a concave mirror. So that means that my focal length is going to be positive. The center of curvature is 8, so my focal length is positive 4. Okay? And then I want to know what is Q. Well, this is all I really know. So this is equal to negative Q over P, and this is equal to 1 over Q minus or plus 1 over P, the inverse. And then I have to solve this system of equations for Q. In order to do that, I'll take this one and say P is equal to negative Q over 2. Then I take this and plug it in here. So you have to solve this system of equations. So I get 4, which I'm going to go back to my fractions. 1 over F equals 1 over Q minus 1 over P, which is going to be 2 over Q. See, P is equal to negative Q over 2. But when I put negative Q over 2 in the denominator, it comes up to become negative 2 over Q. Let me write that over here. 1 over negative Q over 2 equals negative Q over 2. All right, and then I solve for Q. 1 over Q minus 2 over Q is negative 1 over Q. So Q is equal to negative 4. So it's 4, not B, not D, not E.
Like look to your right here, on number 19.
Right over here?
Yeah.
Negative Q over 2. I put in negative. Oh, yes, I'm sorry. No, this should be negative 2 over Q. Because when I bring it up into the numerator, it flips. So I have negative 2 over Q. This minus this is minus 1 over Q. Okay? And then Q cross multiply, Q is equal to negative 4 in order to make that equal. So if Q is negative 4 for a mirror, that means that the virtual image is on the opposite side of the object. The object is to the left of the mirror, so it has to be A, to the right of the mirror. It's a tricky question. I'm not tricky, but there's a lot that you need to know about mirrors in order to solve that. And then the math isn't trivial. Okay? Y'all good on that? Y'all want to look at the last test? Okay. Anything else from this one? Okay, let's look at the last one. Two lenses, aberrations, more lens problems. I don't remember. I mean, you have a couple of lens and/or mirror problems. I expect you have one of each. I don't remember. Basic stuff about, identifying the type of image that's formed. Fraction gratings. Knowing what's the path length difference for various things. Your ray diagrams. Young's double slit, both calculations and just if you change something, what happens. Interference of waves. Know how much they're in phase or out of phase by angle. This is interference again. Remember, you're looking for the path length difference, and then how much of an increment of wavelength is it? If it's a half wavelength, that's destructive. If it's full wavelengths, that's constructive. If it's in between, it's just something else. Know your basic parts. So here, this was the larynx, but I could ask you about the trachea or the lungs as well. Know your basic parts of the ear.
Do you have to know more knowledge about the anatomy part, like your diaphragm pushes?
No, just basic identification.
Okay.
But same here, like on the ear, you need to know all the parts. The auricle, ear canal, tympanic membrane, the ossicles, the bones, the cochlea, station 2, the auditory nerve. I think most of you probably know this. If you don't, you need to know. Well, you're culinary, but everybody else needs to know it. You don't need to know the parts of the ear. Okay? These 23, yeah. Okay, 23 is identical to 15. They're identical. So what you're looking for, I have two sources of waves. I have one over here and one over here. And they're traveling to a point, and I want to know, do I get destructive or constructive interference? And what's important is the path length difference. I'll call it PD. What is the path length difference between those two waves? Because if one travels a little farther, when it gets to that point, they'll be out of phase. And you want to know how much they're out of phase. So here, they traveled 8 meters and 12 meters. 8 meters, and then this is 12 meters, which means my path length difference is 4 meters. 12 minus 8 is 4. Now you want to ask yourself, how much of a wavelength is that? Well, the wavelength is 2 meters. 4 meters is 2 wavelengths. If I'm out of phase by 2 wavelengths, I get constructive interference, right? I have my first wave. My second wave starts a wavelength later, or 2 wavelengths later, or 3 wavelengths later. Then I get constructive interference. If I'm out of phase by a half a wavelength, this means it's going to be like this. I get destructive interference. And if I'm out of phase by any other amount, you get something in between. So if it's a wavelength, or some increment of a wavelength, it's a loud sound. If it's a half wavelength, so like if this came out to be 1 meter, for example, or 3 meters, or 5 meters, then you would get no sound at all. And if it came out to be, I don't know, 2.5 meters, you'd get a quiet sound, meaning something in between constructive and destructive interference. And that other one, 15 or 19 or whatever that was, is exactly, you work it exactly the same way. You'll see one of those, so make sure you get it right this time. Interference. No, because if it's 2.5 meters, the wavelength is 2 meters. A half a wavelength would be 1 meter. In order to get destructive interference, it's going to have to be like 3 meters, or 5 meters, or 7 meters, or 9 meters. Some increment of half wavelengths. All right? Anything else stand out to you on this? This is all pretty fresh, I think.
The 28.
So basic wave properties, and you'll have, I'm pretty sure you have some of this. This is my speed, this is my wavelength, and I want to know its period, t. That's the time. Be careful, there is another t in this section for tension, for the frequency of a string. But my speed is wavelength over period, distance over time, meters per second, and I'm looking for t. So t is lambda over v, which is going to be 0.1 over 3 meters per second. So the units cancel and give us seconds. Third of 0.1 is 0.03. So B is the right answer. Make sure, make sure you can do your basic wave properties. The other thing is V is equal to lambda times our frequency. So if I gave you the frequency instead, you could find the wavelength or the speed. You identify that like at 29. Okay. Any other questions? I'll wrap up otherwise. No? Okay. All right, we'll stop there.